a heartiest welcome to all the participants in-house as well as all the people who have arrived here from a very long distance. I welcome you, all of you. And before we begin this session by our esteemed resource person, Professor Prabir Kumar Biswas, I would like to read out his profile. Professor Prabir Kumar Biswas received his BTech, MTech and PhD degrees in Electronics and Electrical Communication Engineering from the Indian Institute of Technology, Kharagpur in 1985, 1989 and 1991 respectively. He served Bharat Electronics Limited, BEL, Ghaziabad as a deputy engineer during the period 1985 to 1987. In 1991, he joined the faculty of the Department of Electronics and Electrical Communication Engineering at IIT Kharagpur, where he is presently a professor and also holding the position of ESNL chairperson, professor. He is also the head of the Department of Artificial Intelligence and also the project director of AI4I CPS Hub at IIT Kharagpur. Professor Biswas is an additional director of West Bengal Electronics Industries Development Corporation, WEBL. He was the head of the Department of Electronics and Electrical Communication Engineering during January 2015 to December 2020. He also served as the head of the Computer and Informatics Center at IIT Kharagpur from March 2008 to December 2014. Professor Biswas visited the University of Kassel, Lautern, Germany during March 2002 to February 2003 as Alexander von Humboldt Fellow. His research interests are in image and video processing, computer vision, pattern recognition, machine learning and artificial intelligence, IoT, etc. He published more than 200 research papers in various international and national journals and conference proceedings in these areas. He has prepared 5 online video courses under NPTEL program. Professor Biswas is a senior member of the IEEE. He is also the chairman of IEEE Kharagpur section in 2008. He is also a life member and former president of Indian Unit of Pattern Recognition and Artificial Intelligence, India. He is an expert member of various committees of Science and Engineering Research Board, Government of India. He was the domain coordinator of Information and Communication Technology under Imprint. He has served as a member of technical program committees of several national and international conferences and served as organizing chair of Indian Conference on Computer Vision, Graphics and Image Processing in 2008. This is what we understand about the esteemed resource person, and I feel honored to be introducing him to all of you. Thank you very much. Over to you, sir.
Thank you. So I once again welcome all of you to this workshop. In fact, Walash is a student, and possibly he gave my name as an expert before asking me. He was telling me that Chandra said that let me put his name, I'll talk to him later. So that is what the kind of relationship we had or we have with our students. Right? They take teachers as granted. If we request the teacher will not say no. That is the kind of confidence that we have been able to inculcate in minds of our students. It's a great thing for us. And today the whole day is supposed to be mine, except we have one session on paper discussion, right? Yeah, this is something new that I have seen in your program. Discussion on research papers. I did not find it in any other workshop or any course. So that is really a good initiative. And I believe all of you will be really benefited to not only lectures, because lectures at some point of time becomes boring. I was also a student at time. Hearing at the teachers' lectures for hours together at some point of time. So that is a discussion in the forum where you not only listen to the experts, you also can express your opinion. Is really good. So I have 2 parts of my lecture. The first part in the morning half will be the foundations of artificial intelligence and deep learning, where if any of you have got my NPTEL courses on pattern recognition or on deep learning, you'll find that most of the things are repetitive. So that was the foundation one. And as I was not really, did not have any information what's the background of the participants, so I start with the basic one, but I'll make it brief, and the way I have thought of is possibly you will not get bored even if you have gone through it. Okay. Then in the second half, I'll go through, try to introduce what is generative learning or generative model. What are the advantages of generative model? I was also talking about the risk of artificial intelligence. When I go through this, you will realize yourself that what is the risk of generative model. So, for using generative model, one has to be really careful, one has to be really responsible. And then, with some application domains, I will give some application on remote sensing. Of course, I am not an expert in remote sensing, for that Dr. Sharan is there. So tomorrow possibly we'll be talking about what are the AI applications that we use remote sensing, right? So these things together, you'll have a nice package on AI for your remote sensing and art observation, right? So let us start. So the first one is foundation of artificial intelligence. Deep learning comes later. Okay. I always start with this pair of pictures. Like what are these pictures? You will know it. You can recognize it. Possibly yes, because you all have seen these pictures in your history books in school days. Maybe some of you have visited these places. Right? On the left is the Ajanta cave painting. All of you know. This is Parliament building in New Delhi. But now we have a new one. There is the old Parliament building that is there. So the question is not that whether you recognize it. The question is how do you recognize? That is the question. Right. Obviously, you all will recollect that during our childhood, when we started writing or learning the alphabets A, B, C, D, initially the first teacher is your mother, right? The mother started showing a figure on the slate or on the copy, this is what is A, this is what is B, and so that you can remember it easily. It was rhythmic, A for apple, B for ball, things like that. But obviously you could not remember it just in one go, right? The same thing had to be repeated again and again and again. In the process, what you have done is you have created some description out of what you have seen of that particular figure, and that description is stored or modeled somehow in your brain. So that next time, whenever you see a similar such description, you can associate that with the model that is stored in your brain, and then you can recognize or you can associate. It's a sort of association, right? I have a large number of models stored in my brain of different kinds of objects. I'm not saying it is alphabet only. It may be many things, right? So all those different models are actually stored in your brain. And there comes what is the capacity of your brain. Similarly, we have what is the capacity of the model that we are trying to generate. And next time you see any such thing, you try to generate similar such description of the object that you are seeing, and then try to associate this description with the model description that you have in your brain. And wherever you have similarity, we'll call it distance function or loss function. But the distance function or the loss function is least, we associate that object with that particular. So we say this is ball, this is dog, and all. So that is a kind of description that you have to get of. So what are the different kinds of description? So the basic problem is something like this. I have an input signal. The input signal can be a visual signal, like what is this one, or it can be a temporal signal as well. Say for example, speech. We have problems like speech recognition. We have problems of speaker recognition, right? speech to word, word to speech conversion. So these are the problems which deals with temporal signals like this. So what you have to do is, given whether it's a visual signal or a temporal signal or whatever it is, we have to generate some description. These descriptions, which are called features, multiple features taken together becomes feature vector, will come to that, right? So using these descriptions, the feature vectors that we have, using these feature vectors of the known classes, you train your classifier of recognition. And once the classifier is, so here you find that your classifier or recognizer, I can have different types of classifiers. This classifier is domain independent. Whether you are classifying an image, or you are classifying a voice, or classifying anything else. Classifier is not domain independent, not domain dependent. What is domain dependent is this part. It generates the description, right, or generates the features. Using the features, you train the classifier. The classifier, whether you are recognizing an apple, or you are recognizing, say, Hemant Kumar's voice, the classifier is there. Only thing is, which name you are giving to which particular class. That is what makes the classifier to be dependent, otherwise it is domain independent. But this is where you have the low-level processing operation. If I have an image, my processing technique will be something. If I have time domain signal or temporal signal, my processing technique will be something else. The feature vectors, or the features that you generate for images, is different from the features that you generate for temporal signals. That is what is domain dependent. But this part is domain independent. So I have first feature extraction process, followed by training the classifier, and once the classifier is trained, then given an unknown signal or an unknown image, you generate similar such features, give it to the classifier tries to associate this unknown feature with one of the known models which the classifier has already been trained with. And then, on the distance, it recognizes what that object or what that signal is. So that is what is your classifier. Now, what are different types of descriptors that you can have? This workshop being a workshop on remote sensing, where you will deal with mostly remote sensing images, satellite images, whether it is in the optical domain or hyperspectral or multispectral images, synthetic aperture error images. So the descriptors that I'll talk about is mostly in the image domain, right? I'm not going into the temporal descriptors. So here we can have different types of descriptors. The descriptors can be called boundary descriptors or region descriptors. What are the boundary descriptors? It is something like this, right? So you will find that this is the silhouette of horse, this is the silhouette of a zebra, right? But these two silhouettes are more or less similar. Whatever descriptor I extract out of the boundaries, using those boundaries, the descriptors are not sufficient or may not be sufficient to distinguish between a horse and a zebra, though it gives you some information. And these boundary descriptors may be sufficient to distinguish between two different classes. A class of animals contains both horse and zebra. Another class of animals, something else. So I can distinguish a class of animals from the remaining classes. But if I want to distinguish between a horse and a zebra, this boundary descriptor may not be sufficient, because you find the figures are very similar, right? So in that case, you go for some more descriptors. What are these other descriptors that I can use? Which is the region descriptor. That is, what is the property of the region bounded within this boundary, and what is the property of the region bounded within this boundary. And you will find that when you are talking about zebra, the skin, the body is mostly black and white stripes, right? That is what is the texture, which is hardly possible in the case of horses. So along with these boundary-based descriptors, if we concatenate the region descriptors, so what are the different region descriptors that we can use? I'll briefly talk about it. So if you combine these two, you get a higher set of descriptors or a feature vector of higher dimension, using which it is possible to distinguish between a hostel. Right? So coming to the region descriptors, we can have intensity descriptors, we can have color descriptors. There is something which will give you what is called texture descriptors. Right? So what are different intensity descriptors, color descriptors, and texture descriptors we can have? All of you know our histogram, right? So given an intensity image or black and white image, something like this, I can have the intensity histogram of that image. So this histogram is nothing but what is the frequency of different intensity values which are present in the image, right? So this is what is intensity histogram. And when I'm saying frequency, obviously the sum of all the beams, all the units will be equal to 1, right? So as it is frequency, I can consider this as a probability distribution function. What is the probability of occurrence of a particular intensity within that image? So given different images with different intensity profiles, this is histogram. Similarly, in case of the color image, so like this, all of you know that the color image contains 3 different components: red component, green component, and blue component. These components individually are nothing but an intensity image. When I say it is a red component, the meaning red comes from the hardware, not from the data. How you use that particular signal to stimulate the color palette on your screen or your monitor, right? So if you use a particular component to stimulate a red palette, it is a red component. If you use the same one to stimulate a green palette, it's a green component. So the meaning of red, green, blue, that is given by the hardware, not by the data, right? But assuming that, I can have 3 different components: red component, green component, blue component. For each of the components, I can compute such histograms, right? So what is the distribution of the red component? What is the distribution of green component? And what is the distribution of blue component? So I have red histogram, green histogram, and blue histogram. The other one is texture. For texture, I can have different types of computations to extract what is the texture characteristics. Because different textures, we have different characteristics. I'll come to that. So when all these different components are put together in the form of a feature vector, this becomes specific. Using these descriptors, I can distinguish between different figures, right? So firstly, let us talk about how the boundary descriptors that can be extracted. I have taken, say, this carved boundary is the boundary of some object, right? When you compute the boundary descriptor, the first operation that can be done, there are many ways, right? One of the operations can be that I can approximate this closed boundary by a polygon. There are different algorithms for polygonization. So I can have a polygon something like this. So from that boundary, I get this kind of polygon, right? There are different algorithms. I'm not going to that low-level algorithms that how we can have polygonization of a closed boundary. There are multiple algorithms. But what is the property that we can extract from this polygon? Once I have this polygon, you find that in the polygon I have multiple vertices, and in every vertex I have vertex angle. One of the ways is that if I scan this polygon either in the clockwise or anti-clockwise fashion, I have a sequence of those interpolations, which I can consider to be a time series. It is nothing but a series of values, right? So once I have this series, from the series I can extract certain properties. So I have a series, I can form an auto-regressive model of that series. That means, say, an ith vertex angle can be represented as a linear combination of say p number of previous angles, right? So when I am saying previous, the sense in which you are scanning those angles, whether it is clockwise or anti-clockwise, that is important, right? So whether you are making it clockwise or anti-clockwise, it is not that significant, but the significant is, once you decide that you will have clockwise scanning, you should always have clockwise scanning. If you follow anti-clockwise scanning, you should always have anti-clockwise scanning. That is what is important. I mean, it should be consistent. It cannot be that in one of the model I use clockwise, in another model I use anti-clockwise. Then the information is stored, right? So I represent, so this is what is a pth order autoregression. Every angle is represented by p number of previous angles. When I say previous, it is which particular way you have scanned, right? So you find that I get a linear equation from here. So if I have, say, k number of such vertices, for each of the vertex, I will have one such equation. So I will have k number of linear equations. The coefficients of this equation are the values of these betas. Beta 1, beta 2, beta 3. You go for simultaneous solution of these equations, you get values of these autoregression coefficients. And the values of these autoregression coefficients will be different for different vector shapes. Right? So this set of autoregression coefficients that can be used as one set of descriptors. It is not complete, right? Because if I scale up or scale down the same shape, these regression values will remain the same, right? So you get something which is scale independent. At the same time, we have lost some information. If you look at the initial diagram that we had, you find that it had a lot of curves, a lot of detailed information. Those information are lost. It has given me just an average information of how the shape looks like. But along with this, if I want to preserve this carvedness as well in my feature representation, I have to do something more. So this is another example. You have this curved boundary, I have this polygonal approximation, right? So this particular chord, it is nothing but a linear approximation of this segment of the curved boundary. Okay, so I take out this particular segment. So similarly, I have to do it for every other segment. So you take out this particular segment. Then what I do is, I align and orient this segment in such a way that this chord becomes horizontal. Okay? And once you do that, if you normalize this curve, so it becomes a sort of a function fx versus x. Now, if you normalize this curve such that area under the curve will be 1, it becomes something equivalent to probability density. Okay? It tells you, if I put it R versus PR, it tells you what is the probability of R. Because this area under the curve. So once I have this probability, I can compute something which is called statistical moments. Okay, so these are the different statistical moments that I can compute from statistical functions. This is well known. This is something about what is called variance. Okay. The third moment, this is called skewness. Fourth moment is called kurtosis, and so on. So you find that what do they signify? The first one, which is second statistical moment, which is nothing but your variance. If the value of variance is more, that is my spread is more. Spread of the distribution is more. If the variance is less, spread of the distribution is less. It becomes sharper, right? Skewness, it tells you, so suppose I have got two identical distributions. So I have two identical distributions. 1, one is something like this. The other distribution is like this. You find the variance you compute, that is the second order moment, will be same for both of them. But the skewness for these two will be different. So, though the distinction between these two distributions cannot be captured by the variance, but it can be captured by skewness. Okay. So, if you use multiple number of such moments, these moments can distinguish between different shapes. So, what I have to do is, for each of these segments, I compute similar such statistical moments. All these statistical moments put together give you more precise information of the moment. Right? So, using which I can distinguish between different types of quantities. So, you find that all this that we are doing, using this, what I have is a shape converted to a vector. Right? And once it is in a vector, I am in a better position to develop mathematical tools. Just shape in the form of an image, having a mathematical tool. Right? So this is one of the things regarding boundary. Now, what are the different types of region descriptors that we can have? As we said that for this color image, this can be if it is normalized, this is nothing but a probability distribution of different intensity values. Similarly, over here, this is the probability distribution of red components, this is the probability distribution of green components, this is the probability distribution of blue components, and all that. Right? So once it is probability distribution, I can similarly compute all those statistical moments. Right? So statistical moments for some distribution which is this, and if I have another distribution which is something like this, obviously they will be different. Right? At least some of the moments will be different. Similarly, the moments for this, moment for this, moment for this, they will also be different for different distributions. Right? So I compute these distributions, put them together, have it. So those are for color and intensity, but what about this? Texture. It is slightly different, right? It is quite likely that multiple textures will have same distribution. Quite possible, right? So for textures, we have to have a different sort of mathematical tool. The mathematical tool, something like what is this? One of the mathematical tools that can be used is what is called a co-occurrence matrix. Co-occurrence matrix is that if I have two pixels or 2 points, by the way, points in a digital image are called pixels, right? So if I have 2 pixels in a digital image, so you take point P and point Q, with their orientation and distance as parameters, right? And then, what is the value at location P and what is the value at location Q, right? So that is what I'm saying over here. So I have 2 pixels, 2 points P and Q, which are unit distance apart, and the line joining P and Q making an angle 45 degrees with either horizontal or vertical. Again, whether I consider horizontal or vertical, that I have to decide once, right? I and J are the intensity values at location P, J is the intensity value at location Q. So how many such pair of occurrences of intensity values I and J following this geometrical constant occurs in my image, where I and J varies from minimum to maximum. textures, right? Now, if you normalize this matrices, which is called co-occurrence matrix, so that sum of all the elements in every matrix will be 1, then what is this? This is nothing but joint probability, right? And once I have this joint probability density, I can compute various parameters or various features out of this joint probability density. So let us see what those different features that we can compute. One is I can compute what is the maximum probability, right? So you find that I have different such joint probability matrices, one for every positional constant, right? So for each of these matrices, I can compute maximum probability, I can compute what is called difference element moment. Now what is the significance of this difference element moment? I and j in that matrix are nothing but row parameters, right? If I and j are equal, or the difference between I and j is very small, then the value of this quantity, element difference moment, is also very small, right? So you find that if the maximum values or the maximum probability values are centered around the main diagonal, then this quantity will be small, because I minus j to the power k is very small. Whereas, if the larger values are away from the main diagonal, then the value of element difference moment will be large. So this gives you some descriptor, some property of the kind of texture that you have. You are not computing directly from the texture, but you are computing the joint probability density. From the joint probability density, you are computing these values, right? Similarly, inverse element difference moment, which is just opposite to this. Now, because it is a probability density function, I can compute what is called uniformity. I can compute entropy, right? So these values, suppose I have computed, say, 10 number of such matrices. I compute values for each of these matrices. Okay? And these set of values for a particular texture and the set of values for another texture, it is quite likely that they are different if the textures are different. That is the reason that you need multiple number of co-occurrence matrices, multiple number of joint distribution functions, right? And you combine all of them together. That gives you a descriptor of that particular image or that particular object. It combines your shape descriptor, region descriptor, all of them. Now, another important thing that I'll come over here is such texture descriptors can also be computed using transformations, signal transformations. So this particular signal transformation that I have shown is what is wavelet transformation. Wavelet transformation is a very, very powerful tool to extract the signal properties. Because the advantage of wavelet transformation is, I mean, I hope you know about these different transformations, Fourier transformation, discrete cosine transformation, wavelet transformation, and all that. One particular property, specific property of wavelet transformation, which you don't get in Fourier transformation or cosine transformation, is what is the space frequency localization property. If it is a time domain signal, you have time frequency localization. Given a signal, if you take the Fourier transformation, you get Fourier coefficients that tells you what are the frequency components which are present in the signal. But it does not tell you in which part of the signal that particular frequency component is. Right? But in wavelet transformation, it tells you, along with the component, it tells you in which part of the signal that component is present. Right? So in time domain, that is called time frequency localization. In case of spatial domain signals like here, it is called space frequency localization. So, given this kind of, suppose I had a bigger version of this particular image. What wavelet transformation does is, wavelet transformation breaks that signal into multiple number of subbands. right? At the lowest level, you have the frequency components at the highest resolution, right? Then you have frequency components at lower resolution. This is the signal which is the lowest resolution signal. You find that in each of these frequency bands, so this creates one frequency band, this creates another frequency band, and so on. If I go for multiple number of such stages, I get even more number of frequency bands. In each of the frequency bands, you find that you can guess what your actual signal is. That structure properties is that. Had it been Fourier transformation or cosine transformation coefficients, you could not have guessed this. This is because of the reason of space frequency localization power. So in these images, if you look over here, there is intensity discontinuity, right? Here the intensity is less, here the intensity is higher. So any such discontinuity leads to high frequency components. Fourier transformation or cosine transformation would have told me that there are high frequency components in the signal, but it won't tell me where that high frequency component is present. But you come over here, you find that it is telling that there is high frequency component and the corresponding part over here contains high terms. Right? So I can localize where that high frequency component is. So given such a kind of transformations of the transformation coefficients, from each of the frequency bands, I have this frequency band, I have this frequency band, I have this frequency band, and so on. For each of the frequency bands, I can compute what is the energy. Energy is, equivalent of energy is nothing but sum of squares of all the coefficients. So I can compute what is the energy of this component, what is the energy of this component, what is the energy of this component, and so on. Put those energies one after another in a particular order, you can make a vector, right? So it is the energy content of the signal in a particular band or subband. Different signals. They will also have similar energy components, but the same energy component in the energy value in the same subband is unlike. Right? So if I have multiple signals, put this energy components into different subbands in a particular order, I get a vector. This vector is likely to be different for different images. Right? So this is one of the way in which you can compute the texture features. The other one, which is very, very popular, in fact one of the most powerful tools for texture property extraction is what is the Gaussian. Okay. This is what is the kernel of the Gaussian. You find that there are three different parameters. One set of parameters is sigma x, sigma y, which is nothing but standard deviation or variance. Okay. So what is this after all, this exponential term? This is nothing but a Gaussian surface, right? This is a cosine term, cosine omega. So this Gaussian surface and this cosine term, because this Gaussian surface is multiplied by this cosine, which means I have a Gaussian envelope which is modulated by cosine wave. Right? So in one dimension, if I put, it is something like this, that I have this Gaussian envelope, and this Gaussian envelope is, how do I get color?
Below, I think. Bottom. Yes, sir. Here I can change. In the bottom part, sir.
Yes,
No, middle.
this one.
Center, yes, downwards.
Okay. So this is my Gaussian envelope. Now what I could do is, this Gaussian envelope is modulated by a cosine wave. Right? In one dimension. In two dimension it's a surface. The entire surface is modulated by this cosine wave. Right? And then, when you come to this part, x prime, this is what is the rotation. So I have this x prime is equal to x cosine theta plus y sine theta, y prime is x sine theta plus y cosine. So inherently, I have a parameter which is theta, which is telling me that, so here you find that cosine omega x prime, that is a cosine, what is the direction of this cosine? It is in the direction of x prime, while x prime you are taking by the y. Right? So you find that I have three different parameters here. One parameter is the scale, which is variance or standard deviation, that tells me that what is the spread of this Gaussian, whether the Gaussian will be narrow or the Gaussian will be wide, which effectively signifies that what is my region of support over which I am doing the computation. Right? Frequency of this cosine, that is omega, and the orientation of x naught is given by theta. So I have three different parameters. Right? For different combinations of these three different parameters, I have different Gaussian filters. Right? So here you find that this is an instance of one Gaussian filter with one value of theta, so you find that this is, to look at this Gaussian is in the direction of x. That is theta is zero. Right? This is the partial direction for each theta is 90. Right? If I increase the value of sigma, now your Gaussian envelope, modulated Gaussian envelope is only over this region. If I increase the value of sigma, this would be possibly over this region, over a larger region. You increase the value of omega, that is the frequency, the number of such sinusoidal patterns will increase. So these are three different parameters I have. For each of these parameters, I get one such kernel. Now what I have to do is, given this input signal, you convolve that with this kernel. Convolution here is, I want to make a distinction. There are two terms, one is convolution, one is cross correlation. You ask a computer scientist, the cross correlation and convolution they are taken to be different part. That is how you compute. That is how you compute. That is not the difference. So do you mean that if I don't flip, they will be same? No. Convolution says, convolution tells you that what is the property of the system. Kernel, right? And when you convolve, if I have a system with this property, give an input signal, what will be the response of the system? That is what is convolution. Cross correlation, as the name correlation suggests, given two different signals, what is the similarity between these two signals? Convolution is not similar. It may not be peak. You will get a peak only when the system response, the system characteristics matches with the input signal. Then only you get a peak. Otherwise you will not. But whatever it is. So if I convolve this image with this particular kernel, I get this. Right? I'm specifically talking about this convolution because my next part is going to be on convolution only. today's artificial intelligence or machine learning is fully based on convolution.
Sir, it will affect if you increase the size of the kernel.
Yeah,
Largest.
it will affect. It will affect because then you are computing over a large
Large
area.
area.
Right?
Allowing larger
So
area.
when you are doing convolution, I'll come to that, how convolution is complete. Similarly, if this is then this is the response. Right? So you find that your response is different for different type of things. Right? So I can have, by varying sigma, omega, and theta, I can have different types of kernels. Each of the kernel will give you some response for a particular signal. For another signal, for another image, the set of response will be something else. Right? So now what I can do is, for each of these responses that I get, I can compute the energy. Right? The set of energies over different kernels that you get, put that in a particular order. If my input signal or the input energy is different, the set of energies will also be different. So that is another kind of descriptor that you can use for distinguishing between different types of textures, right? So this is another thing that we have. So what we are having is, we are having a set of feature vectors, okay? So for, if I have an image of bodies, so now I'm assuming that, let us take a hypothetical situation that I have two dimensions. I have two feature components, one is x1, the other one is x2, right? x1 may be something that you have computed from one kernel of Gabor filter, x2 is from another kernel, right? I have taken this assumption, this particular hypothetical case, so that I can plot it on the board, right? So this is what I have one image, that is image of the part, and suppose the feature vector x1 and x2 values that I get, that is placed somewhere, right? The next one, another part. So feature vector that you compared will be similar to the previous one. So they will be close, right? Why not identical? Why they are not mapped to the same point? The reason is, you think of any natural process. You think of when you have drawn your engineering drawing. I think all of you have done engineering drawing, right? How do you specify a dimension? Let us come to something natural. Okay, you are from the, anybody from engineering background? So this mathematics is okay for you? Okay. Suppose I want to draw. So I think I should go a bit slow, right? Suppose it's cylinder, right? Being engineers or designers, your purpose will be to put the dimension in such a way that the fabricator will be able to understand, set the machine and get it the part, right? So if it is a cylindrical block, it has two dimensions. One is length, other one is radius or diameter. Suppose I want the length of this block should be 1 meter, right? So I write L is equal to 1 meter. If my unit is meter, I'll put it as 1. Radius, suppose I want it to be centimeter. So I put it as 0.05. Is that enough? No fabricator in the world will accept your drawing because it cannot be achieved. Along with this, you have to specify, say, plus minus 0.001, something like this. I'm taking just an example. Plus minus 0.001, right? Which is the tolerance. I want 1 meter, that is fine, but plus minus 1 millimeter is acceptable. That is what a fabricator will accept. Because every manufacturing process has a tolerance inbuilt. If I say 1 meter, I will hardly get a dimension of 1 meter. Okay? So that is the tolerance which will be taken by the machine. The machine is not perfect. Right? Similarly, given two different persons, myself and Prof, let us assume. You can identify us, right? And PKB, he is Prof. Both of us are human beings. So if you compare my feature, my shape feature and his shape feature, both of us being human beings, the shape feature should have been identical. But it is not, because there is a variation. Right? So because of this variation, whether it is in the process of manufacturing or even in the process of development. Suppose I give you a scale, an inch scale, which has a subdivision of 1/10th inch. Let me go to the centimeter scale. You have centimeter, within that you have 10 millimeters, right? If you have been given an item which is a 5 centimeter and say 0.3 millimeter long, I ask you to measure what is the length of this element. Will you write 0.3 millimeters? So 5 centimeter, 0.3 millimeter. Will you write 0.3 millimeters? All of you have done your experiments. Library experiments. If you write 0.3 millimeter, 0.3 millimeter, your examiner will give you 0. Though your answer is correct, but you will get 0. The reason is, given your measuring instrument, you cannot measure 0.3 millimeters. Right? Either you can measure 4 centimeter exact or 4 centimeter 1 millimeter. In between 0.3 millimeter, I cannot measure. That is your error in measurement. And that measure has a variance, has a variation from 0 to 1 millimeter. So that is the imprecision that you get both in manufacturing as well as in measurement. Right? So because of this, even though both are parts, the feature vectors that we compare, these feature vectors will not be identical. It will be slightly different. But because the other features are similar, they will be close. Right? Similarly, a third part. Now if I have a car, again I am getting the same feature vector. But now, the feature vector of bird and feature vector of car, they will be wide apart. So the car will be placed somewhere. Right? Similarly, another car, it will be close to this, but away from this. If you have a dog, I'll have a feature vector somewhere over here, another dog. So if you carry on like this, you will find that all the feature vectors belonging to a particular class of objects, they form a cluster. Feature vectors belonging to a particular class of objects, another. This forms another cluster. That means I have a distribution of feature vectors in the feature space. And this distribution is going to be different for different classes of different objects. Right? It is not identical, same point, but a distribution of points. So once I have that, now my classification conceptually is very simple, right? I have one distribution here, I have one distribution here, one distribution here. Then what my classifier will learn? The classifier learns the boundary among different distributions, right? So I call this is region A, this is region B, this is region C. For getting this boundary of the regions, I have to have feature vectors, large number of feature vectors, from which objects those feature vectors have been computed, they have to know. Because using known feature vectors, I am generating my classifiers. Like what my mother taught me, shown a drawing, shown a diagram, told that this is what is A, right? So you are giving a data along with the class, what it is. And through that only I am learning. Once I learn, then another A shown to me may not be exactly same figure but slightly different figure. Gets a different description but similar. Now I know that in which of these regions that particular figure will be. And based on that region information, I identify what this object is. Right? It works exactly the same way, conceptually. But how my brain maps all those things, stores all these informations, even today, though we are working on neural network, that will be our next topic, we assume something, but no one knows whether that is exact. It is our approximation, our intuition, so that is how it works. Okay. So this is what is my classifier. So effectively, what these feature vectors give me from the known classes is what is called Px given omega I. That is what is called class conditional distribution function. Okay? Where x is the feature vector, omega I is the particular class. This may be a dog, this may be a car, this may be something else. Right? For each of the classes, I have some of these distributions. Now, given these distributions, now I have to design a classifier. Right? So that classifier, the very basic one is what is called base classifier. So what have been given? I have been given P of x given omega I, that is these different distributions, which you have computed from the large number of training samples for which I know the classes. Right? So what Bayes' rule says, this is from basic probability theory. Machine learning people have adopted it. There is not a contribution of machine learning people. Right? So it says P of omega I given x. Because once my classifier is trained, then what I want to do is, given an unknown feature vector x, I have to identify to which class this feature vector x belongs. That means what I have to compare is P of omega I given x, where x is unknown. Right? What is known to me? X given omega I, that is the probability distribution function of different omega I. P omega I is something what is a priori probability. It is domain dependent. In the sense that if my problem is you differentiate between, say I have a manufacturing unit where I manufacture different machine parts. Right? Some of the machine parts will be correct, acceptable. Some of the machine parts will be faulty. It is quite acceptable, right? I mean, not that everything that I produce will be acceptable. But it is quite expected that the number of machine parts which are accepted, the number of that will be much more than the number of machine parts will be rejected. That means both these classes have some a priori. The probability of a machine part being accepted is much more than the probability of a machine part being rejected. So that is what this P omega I tells, that what is the probability of occurrence of a particular class. Right? So this basic base classification is P of omega I given x is x given omega I into P omega I upon P of x. Right? This is the one which is already computed by designing the classifier. Now I have to compute this P of omega I given x for different values of I, because I have different number of classes. because otherwise, even this whole day or even this entire 7 days, I'll not be able to complete the first part of this. So you get a feel like how the classifier actually works, right? So this is what we have. These are all mathematical details. I think I leave the slides. You can distribute them. So anybody interested can go through the mathematics. Yeah. So this is something very important. So given two different distributions, right? If I have only two classes, then what the classifier is learning is what is the boundary between the two classes. Once I have this distribution, for every distribution I have something called what is covariance matrix. If it is a single variable, it is variance. That tells you what is the spread of it, right? But now I have feature vector which has got multiple number of features as elements in a vector. So it is not just variance, it is a covariance. So I have to compute what is covariance matrix. And the covariance matrix actually tells you what is the spread of data over the feature code, over the feature space. Right? Now given two classes, I and j, if that
it looks like learning with prototypes.
learning with,
So
I'll not say prototypes, you are learning with data, effectively translating that prototype. Right? Because I don't have a prototype, what I have is raw
you have
data.
data, they are creating something.
Out of that, finally, my classifier happens to be prototype-based classifier. How I come to that? So if the covariance matrix between the two classes, omega I and omega j, they are identical. Right? If they are identical, then the classifier that I have is something like this. It's a linear. Okay? In a specific case,
Sir, then this linear line should be perpendicular to this.
I am just coming to that.
Oh,
Not always. If this covariance matrix is of the form sigma square I, where I is unity matrix, so you find that this is a matrix where I have covariance matrix like this, sigma square, raised over
all are zeros.
What does that signify? The feature components of the feature vector are statistically independent. Right? What does diagonal tell you? X11 square, not eigenvalue. Okay, finally it will come out to be eigenvalue. Right? X11 square, sigma 11 square, sigma 2 square, sigma variance of individual components. Right? So it says the components are statistically independent. Variance of every component is same. Right? If it is so, what is the nature of the distribution? It is hyperspherical distribution. Right? If it is a hyperspherical distribution, and I was talking about a priori probabilities, P omega I and P omega j. If the a priori probabilities are also same for classes omega I and omega j, then this boundary will be a perpendicular bisector of the line joining, this is mu I. Mean of class omega I, this is mu j. It will be a perpendicular bisector of the means of the classes. Right? And effectively, your classifier becomes a minimum distance classifier. The reason is, I have mu I over here, mu j over here, there is a line joining mu I and mu j, this is the perpendicular bisector. Now if I have an unknown vector x which is coming somewhere over here, the unknown vector is being classified to mu j. It is on this side of the boundary. In other words, I can say that you compute what is the distance from mu I, what is the distance from mu j, whichever distance is less, similarity is more, you are classifying to that vector. Now coming to your prototype.
Sir?
Given this, mu I and mu j, they are nothing but the prototypes of the classes. Right? So eventually, you are creating a prototype, but you are not learning this prototype. Right? So this is the case when mu I and mu j are of this specific point. It will be a bisector, perpendicular bisector. Right? In all other cases, my sigma I and sigma j are identical, but not of this one. Then my bisector will not be a perpendicular bisector. Okay. It will be a straight line, but not perpendicular. This also a minimum distance classification. But the distance that you compute, in this case, the distance that you are computing is what is called Euclidean distance. Right? In this case, if my x is somewhere over here, its distance from mu j will be less than distance from mu I, but this distance is not Euclidean distance. This distance is named after a statistician, Mohalari distance.
Where W is?
Yeah. Right? I'm also taking American distance. Yeah, you are asking something else possible.
No, sir, that distance I am talking about. The new point x coming.
Yeah.
So x minus mu j.
Right.
It is in the equilibrium distance. So then minus I and equal to 0.
However, if sigma I is not fixed, then my classifier is not a linear classifier. That comes from computation of, see this particular term, it tells you why this crossover point will be. If P omega j, this is my class omega j, say. If P omega j is greater than P omega I, that means more number of samples will be classified to omega j. Its probability is more. If P omega I is greater than P omega j, then more number of samples will be classified to omega I, not to omega j. So, if P omega j is greater than P omega I, this will shift towards left. Because you have to have more space towards class omega j. So the crossover point will be towards mu I. Right? This will be the midpoint of the line joining mu I and mu j if P omega I and P omega j are same. Okay. Now if you look at this, if omega j and omega I they are same, but x transpose mu j inverse x and x transpose mu sigma, not mu j, sigma j inverse x, and x transpose sigma I inverse x, they will cancel each other. As a result, the equation that you will get is a linear equation, right? And that is what gives you this. Okay. If these two are not same, then I'll have a term x transpose. If you expand upon this, I'll have a term x transpose mu j minus mu I inverse x. There is a term which will be remaining. Okay? And this is what is a quadrant. It is not linear. X squared. Right? And that is what makes this classifier unknown. It's a quadrant classifier. It is not a linear classifier. Is that okay? I think I am too much into mathematics. So this is the basic concept of classifier. I will just skip all this. So the one that we are going to talk about is what is the neuron. Right? So these are the basic concepts will be known to you, right? How presumably the neural processing in our brain or your entire sensory system works, right? And we assume that our neural network that we plan to design works in a similar way, but no one knows, right? It works reasonably well, but our system is much more complicated than what we think. So basic neurons are something like this. It has a number of sensors. Every sensor is giving some input, which are collected through the action set. They are gathered into a code, which is my neuron. The neuron makes weighted sum of all these elements and then performs some nonlinear operation on it. So mathematically it can be put as if all these weights are represented by a weight vector W and my input is a vector X, I have different components, right? Feature components. So X is a feature vector. So effectively what I am computing is W transpose X. Every feature being weighted by the corresponding component of weight vector W and add them. And then perform a nonlinear operation. That gives me the output. And this is what is given by an individual neuron. Right? What are these different types of nonlinearities I can have? One type of nonlinearity is a threshold nonlinearity. That is, if some weighted sum of all the inputs is greater than 0, my output will be 1. If it is less than 0, output will be 0. So this is what is threshold, hard threshold of nonlinearity. But this has a problem. If I use this hard threshold of nonlinearity, my training of the neural network becomes difficult because training is a differential process, and this threshold is not a differential, right? So approximation of this, you use the regression function, the sigma delta function, but it has its own problem. We'll come back later. Okay, so this function can be written by this particular expression. You need not write the expressions, I leave the slides. Okay. So this is the kind of nonlinearity that I can have, and this is the model of every individual neuron. When I talk about neural network, this is another kind of nonlinearity, which in modern machine learning, we call it deep learning. Instead of using, that is the problem that is said, that of the sigma delta function, which can be avoided by this, what is called REM, rectified linear unit. This is another nonlinear.
This is also one side bounded.
That is why nonlinear.
Yes.
Otherwise it's a linear, right?
Yeah.
So this is why it is called rectified linear unit, right? Because of this only it is nonlinear. So this is the kind of application function that is used in our deep learning networks. Okay. This is just one of the addition. There are other things as well. We'll talk about that. So a neural network becomes a network of all these individual neurons. Right. So typically it is a hierarchical one. You collect the inputs, at every layer the information is processed, take the weighted sum of the inputs, pass it to the nonlinearity, the output of every neuron is fed to the input of the neurons at the next level, so for next layer. So I have multiple layers of inputs. This is what is called multi-layer perceptron or NLP. I think I'll skip this. Or I'll just scan over this to tell you that why multi-layer is needed, right? So this is a function, anybody from electrical sciences?
So
electrical sciences. So you know these different gates, like AND gate, OR gate, and all that, right?
Digital electronics. You know the digital
Digital
electronics.
electronics, right?
It is also in the computer science.
It is also in the computer science, right? But not in biology. So it is something like this, that I have a unit having two inputs. So for computer science, I am putting it the other way. These two inputs are two activations or two signals, right? AND gate is something that I'll activate output only when both the inputs are present. If any of the inputs is absent, the output will not be activated. So I put it like this: activation is 0, or input present is 0, input absence means 1. Absence is 0, present is 1. So if both the inputs are absent, obviously I will not activate output, so I will put in 0. Only when both the inputs are present, then only I will activate the output. Right? This can be modeled as a classification problem. How classification problem? I can consider these inputs as two-dimensional feature vector, where the features are binary, either 0 or 1. So only when input is 1, 1, a particular feature vector, I have to activate this. So it equals to activation class. Any other input pattern, it is a different class, which is I can call it sleep class. Something like that. So this is a classification problem. If it is a classification problem, then I must be able to design a classifier. Here you find that if the input is 0, 0, my output is somewhere over here. 0, 1, 1, 0. Or 0, 1, 1, 0. If it is 1, 1, then output is 1, 1. Right? So I can have a boundary between these two different classes. This boundary is nothing but a state. Equation of the state line can be many. This is one of the equation, that x1 plus x2 minus 1.5 equal to 0. How does it help? If both of them are 0, computed value is minus 1.5, think of threshold function, less than 0, so similarly 0, 1, if it is 0, 1 or 1, 0, the value is minus 0.5. Again less than 0, only when it is 1, 1, the computed value is 0.5, greater than 0, so output becomes 1. So this is the classifier. Now this classifier can be designed using a neural network. I am not going into mathematics. x1, x1, 1, that is the bias. Weights are 1, 1, minus 1. Take the weighted sum of this, it becomes x1 plus x2 minus 1 into 1.5. That is my computed value. Apply the threshold into the output. Is that? Similarly for the OR function. Again, it's a linear classifier. I can implement this again using neural network, but now the weights are different. x1 plus x2 minus 0.5 is equal to 0. That was the equation of the state line. So I can have this sort of result, which includes OR function. Think of something which is XOR function. XOR function says that if the inputs are same, the output will be 0. If the inputs are different, then the output will be 0. That means if the input is 0, 0 or the input is 1, 1, in both the cases my output is 0. If the input is 1, 0 or 0, 1, then the output will be 1. How to get such a classifier? Now, your two classes are not separated by a single straight line, but the two classes are separated by a single straight line. Okay, I cannot have a single neural network for one class. So again, this XOR function can be written in two levels. This is same as x1 or x2. x1, this is actually a NAND function, and invert. Okay? which is equivalent to this. I have these two functions, take AND of these two. That gives me an example. That means I can now have my network in two different layers. In the first layer, I have two different neurons. One neuron will compute OR. We have seen how to do it. One neuron will compute NAND. NAND is nothing but inverter. Right? So in case of an AND function, our function was x1 plus x2 minus 1.5 equal to 0. That was bounded. For NANDing, I'll just invert it. I'll make it minus x1 minus x2 plus 1.5. That is my NAND function. So simply by inverting the weight vector, I can implement an AND function, but it can be implemented using single neuron. The second level neuron will be ANDing operation of these two. Okay? So my neural network will be something like this. One of this will compute x plus the OR function. The other one will compute NAND function. At the second level, you take AND, this is another AND function, ANDing of this output and this output, that will be the function. Okay, because it is not linear. So it simply says that if my classifier is a nonlinear classifier, I cannot implement a nonlinear classifier using a single layer. I have to have a polyphonic system. I have to have multiple layers to implement a nonlinear. Okay. So depending upon the kind of nonlinear, so effectively what it gets, all the neurons, every neuron in the first layer gives me a linear classifier. That is a linear classifier. Right? I have multiple neurons, so I have multiple linear boundaries. In subsequent layers, what you are doing is, you are combining these linear boundaries in such a way that given a nonlinear boundary, the nonlinear boundary is represented by piecewise linear boundaries. Okay. Simply, I'll take an example, something like this. Suppose I have say this is the portion which belongs to one different class, and so this is the one which belongs to one class, and this is the one which belongs to another class. So my boundary will be something like this. I can implement this by a combination of two boundaries. So one of the boundary will be this, the other boundary will be this. Right? So this linear boundary differentiates between this class and this class. Okay? All the points coming to the left of this, from the points coming to the right of this. This linear boundary differentiates between this class and this class. All the points to the right of this, all the points to the left of this. So now my logic can be that if I have a point to the right of this line L1 and to the right of this line L2, that is my class omega 1. All others are in class. Right? So this classifier using first level neuron, this is using first level neuron. The second level neuron combines these two following this logic to the right of this and to the right of this. Right? So for a nonlinear boundary, I need minimum 2 layers. And if I increase the number of layers, along with that nonlinear activation, more and more complicated boundaries get formed.
And you said increasing the layer, degree of nonlinearity will increase.
Degree of nonlinearity will increase. Okay. So that is what a typical neural network is, right? You have the input vector x, passing through the first layer, suppose it is giving a function f1, so you get f1x, which goes to the second layer, so you get f2 of, not x, f2 of f1x. Then you get f3 of f2 of f1x. So it is one function embedded into a series of functions. Okay? So finally, your output will be something like this. Fk of fk minus 1 of fk minus 2 and so on at the lowest level at f1 of x. That gives you the number. Okay. How do you implement each of these functions? Nothing but weight vectors. From one layer to another layer, the neurons are connected via weight vectors. So by training this classifier, what I mean is, I have to choose the weight vectors, right? But how you do it? That is what is your training algorithm. So the training algorithm is, I'm not going into details of this. So suppose this is one of my neurons. I have a large number of layers. In every layer, you have large number of neurons. From every layer to the next layer, they are connected by weight vectors. Right? Now, when I'm training this, then as we said before, that I have to feed in feature vectors for which the class is known. Right? Using that only I train. So, suppose I feed a feature vector x for which I know what is the corresponding class y. That means this training data has to be fed as a doublet x what? Where x is the feature vector and y is the class. Right? I feed in an image. If it is image of a dog, along with that I will say it is a dog. If my image is that of a lotus, along with the image I have to say that it's a lotus. Right? The network, I get the output from the final layer. Suppose this is the output for dog. Right? So if I feed in x for a dog image, it is expected that this output will be high, ideally 1, all other outputs will be 0. Similarly, if I say that this is the output in between, which is for lotus, if I feed in image of a lotus, I expect this output should be 1, all other outputs will be 0. If I get anything else, suppose I feed in dog, but an output for cat becomes 1. The dog output is low. That is an error. I know it is error because I know which image I have fed in or which feature vector I have fed in. So I can always, so that is, one of them is called a target vector because this output is nothing but a vector. Only one component of this vector is likely to be 1. The other components are likely to be 0. Or one component will have a high value, the remaining components will have low value. I can get 1 and 0 if I use threshold nonlinearity. If I use sigmoidal nonlinearity, that gives me some sort of probability. Right? So given this input, what is the probability that this input belongs to which particular class? So that is the posterior probability P of omega phi given x, that is what is given at output. Then how do you train this network? So am I giving you something useful? For you, it's a repetition.
So I only did from your class, the FCDL classes.
Okay. So for a given input, I know what is the output. That means I know what is my target vector. Right? But If the network is not proper, minus d is the error at the output channel. Okay? What I compute is the squared error of t minus d, and you train the network following a gradient descent procedure, because you find that this d is nothing but my x is fixed, right? I've given x, so it is fixed. Output is a function of the input that you have fed and all the weight parameters through which it is possible. Right? My x is fixed, activation functions are fixed. What I want to train is the weight vector values. So my output d or t minus d, because t is fixed, t minus d or d will be a function f of x and all these parameters taken together, let me call it a set of parameters of which x is fixed. So my output, this t minus d, becomes a function of the set of parameters theta. If I vary theta, output will be different. Okay, so my output or the error, that becomes a function of set of parameters. My training is that I vary theta in such a way that this error will be minimized. Target this error has to be 0. I may not be able to achieve that because getting error to be 0 is too optimistic. It is too specified a system, but I'll try to minimize. Okay, so for doing that, the process is that let me put it something like this. Again in one-dimensional form. So this is my error, which is t minus f. This is theta, that is the set of parameters. Right? If my theta is properly chosen, set of theta is proper. I'm not going to the details of analysis, giving the concept. Right? If the set of parameters theta is properly chosen, then my error will be minimum. Theta, anything from that optimal value to the left or to the right, error will increase. Right? So my error function E for different values of theta is something like this. This is the optimum value of theta that I want to achieve, I want to attain through the training approach or learning. Right? So for this, what I do is, I take the derivative of E. Hope you know what is derivative. Right? So I take derivative of E with respect to theta. Right? At this point, derivative of theta, E with respect to theta will be 0, because at minimum or maximum it is 0. At this point, derivative of theta will be in this direction, will increase in this direction. If I increase theta, f also increases. In this region, if I increase theta, E will increase. Right? Now, if I assume that at some point of time, I have a theta which is something. Right? I take the derivative of E with respect to theta. The gradient is positive in this direction. So I have to reduce theta by some amount which is proportional to gradient. That means I have to move in the negative direction of the gradient. So this is what is called gradient descent procedure. Right? So my parameters theta has to be modified as theta gets at any particular stage, if the value of theta was theta I, the next value of theta, which is theta I plus 1, will be theta I. Now I have to go in the negative of the gradient direction. So theta I minus del theta, del T del theta with put a constant, or which is called the rate of learning or rate of convergence, which is theta. This is my training algorithm. This theta is very, very crucial. How to choose this theta, that depends upon your experience. Because theta tells you, so here I had theta I minus 1, I plus 1 is theta I minus theta times del E del theta. So if this theta is very high, maybe I overshoot my optimum point and convert. Right? So if theta is very high, I will have oscillation around my solution. If theta is very low, then maybe I come over here, then come over here, then come over here, like this. So your rate of convergence will be small. Okay. So this is what is your training algorithm. This is how you train your algorithm. Okay. All these mathematical details, I'll skip that. The slides will be written. So these are different loss functions. The first one, that loss function I say is, that is what is called square loss, t minus d square. Another loss function that has some problem. To solve that problem, to mitigate that problem, there is another loss function which is called loss intervals.
So what is D in T minus D?
T is my target. D is what you get output. Yeah, the error is T minus 1, right? So again, I'm not going to details of this. This is how to compute the cross entropy. Yeah. So here you find that the neural network that I said, my assumption was input to the neural network is the feature vector. Right? I'm not giving raw signal. I'm not feeding in an image or an audio signal. I'm giving the feature vectors. The feature vectors are computed using the previous methods that we talked about. Right? Boundary based or region based, say color descriptors, or so that is, those are what are known as handcrafted features. So you compute the feature vectors, give that feature vectors to the neural network for training. Once the network is trained, give an unknown feature vector of an unknown image or object to the neural network. If the neural network is properly trained, it will be able to tell you what that object is. Okay. So these features are called handcrafted features. Now let us see. We want to recognize this. What is this? That. You all are sure it is that, but you have some doubt. Okay. This is what is Taj Mahal. This is what is a very, very challenging example. A very, very challenging problem to train. Right? Using the handcrafted features, because whatever features, say age-based feature or whatever color, texture, they are more or less like. So it is really a challenging problem to train a classifier to differentiate between a Taj Mahal and Biblical. Okay. So I cannot think of any handcrafted feature. So there comes the concept of machine crafted features. That means, can I design a machine, something like a neural network, which will on its own, one thing, decide that what kind of feature it wants to use. I'm not right? So there is a neural network which is called autoencoder, which can perform this task. Autoencoder, so now this X is not a feature vector, it is the raw signal that I am giving as input to the autoencoder. Autoencoder output is again a raw signal. So instead of X, x hat. That is approximate value or approximate reconstructed x. Okay. At the input you are feeding in x, that is the signal. At the output I want this reconstructed x, which I expect that it should be identical x. My information flow is something like that from the input layer neuron. It passes through, this is what is called a bottleneck there, but the number of neurons is much less. Because in case of feature, that is what we have done, right? My image may be